In this video, we're just going to work through a nice example problem that involves sort of everything we've learned to date, or most things anyway, um, with respect to forces. It's going to involve all three Newton's first and second and third laws, as well as our problem-solving strategies and everything. And hopefully, this will be very useful in helping us get comfortable with how to do these things. So the problem is this. Consider a situation shown below. So in this figure here, where a two masses, M1 and M2, one 7 kilograms, one 20 kilograms, and both are connected by a rope over this frictionless pulley. And they're, the question asks, what's the tension in the rope? And what is the acceleration of those two boxes? And there is some friction here, so we're going to assume that they are actually moving, and that the coefficient of kinetic friction is 0.18. The other assumption is we're going to assume that these the rope and the pulley are both going to be massless. So how do we do this, right? So I'm going to again just harp on this problem-solving technique that Knight talks about, but the first step is ID forces, right? So what are the forces that we're concerned with? Well, we're going to have to pick an object, right? So let's start with mass 1. So to identify the forces, we circle mass 1 and we look at anything that breaks that circle. So we know everything touching mass 1. And we have the rope, so there's a tension on mass 1. And we have the surface of the ramp or whatever this thing is. So if there's a surface touching it, surfaces can have friction and a normal force, right? So those are the only two things touching mass 1. So now we move on to long range forces, and there's gravity, right? So for mass 1, we have friction, the kinetic friction, the normal force, tension, and gravity. So step 2, once we've identified all the forces, is to draw a free body diagram, right? So let's look at mass 1. We know the normal force is always going to be perpendicular to the surface of that's applying that force. So it's going to be straight up. We know tension is always going to be in the direction of the rope or the wire or whatever is pulling on that object. We have gravity is going to be straight down towards the center of the earth. And then kinetic friction. Presumably this is going to be moving to the right, so we are going to have some kinetic friction off to the left. So we've got our free body diagram for mass 1. And again, we're just brute force walking through these steps, analyzing objects. The third step is draw a coordinate system, because we're going to have to break these objects down, or these forces into components. So I think our standard X and Y coordinate system is going to be probably the best way to go about this one. So that's step 3. Fourth step is, the mathematical one. We're going to apply Newton's second law, F net equals ma, in that coordinate system, right? So in this case, we have, in the x direction, F net x is equal to mass times the acceleration in the x direction. So then we can look at all of these forces and consider what are the x components of them. One thing we notice in our coordinate system, the normal force and the force of gravity are both in the y direction. They have no x components, so they're not going to come into this equation. We have T1 in the positive x direction, so we have T1, and we have the kinetic friction in the negative x direction. And those are going to be equal to mass times the acceleration in the x direction. And we don't know what that is. Presumably these are going to move, but we can't, assume it's 0 or anything like that. But we've figured out one equation that describes, this part of this system. It's given right here. If we look in the y direction, let's just draw another thing here. F net in the y direction is going to be equal to mass times the acceleration in the y direction. And, with this coordinate system, our friction and our tension have no y component, so they're not going to come in here. All we have is a normal force upwards minus mg, our force of gravity, downwards, and this is going to be equal to mass times acceleration in the y direction. In this case, we know that this block here is going to be moving left and right on this surface. It has no acceleration up or down. It's not jumping off that surface or anything. So we actually do know that this acceleration is 0 in this case. So this equation can then be solved for the normal force is equal to mass times gravity. And this is the normal force on mass 1. Should probably be explicit with some of these subscripts, right? So this gives us our second equation. Now, we can do a bit more here. If we recall, we know that kinetic friction is equal to the coefficient of kinetic friction times the normal force. So we can make that substitution into equation 1 here that we solved. And then we have T1 minus mu k times n is equal to mass times the acceleration in the x direction. And since we know this normal force, we just solved it here with equation 2, we can plug that in as well, and we get T1 is equal to mu k, and this is going to be m1, the mass of that object, times g, because that's our normal force. Got way ahead of myself there. So this should actually be t minus. That is equal to mass times acceleration in the x direction. So again, we've used our model for kinetic friction, how we can quantitatively calculate the magnitude of the force of kinetic friction, and we've used equation 2 here to solve for the normal force. Now, that's all well and good. We've got one nice equation here from looking at mass 1, where we put this equation 1 and equation 2 together, but we're still kind of stuck. We have T1 and AX are both unknowns. They're both things we don't know, so we can't really solve this yet. So we're going to go back and just keep analyzing more and more things, right? So the next step in our problem solving sort of brute force method here is pick another object. If you don't have enough information or enough equations to solve for what you want to know, pick another object and repeat. So that's what we're going to do now. We're going to pick mass 2. And if we look at mass 2, we're going to go through these same steps here, 1, 2, 3, and 4, but we're just going to do it on mass 2. So identify the forces. Well, same sort of thing. We have a tension on block 2 because the rope's touching it. It's touching a surface here, so there's a normal force for block 2 and a frictional force for block 2. And of course, we also have the, the long distance force, or the long range force of gravity, right? So we've identified all the forces, tension, friction, normal force, and gravity. Now we're going to draw a free body diagram, step 2. Now again, I like to draw sort of a line for that ramp just to, so I can orient myself. And there's my block mass 2 here. I'm going to write mass 2 up here so we can keep things straight. And I'm going to label all my forces. I know the normal force is always perpendicular to the surface applying it, so that's my normal force. I know tension is going to be in the direction the rope is pulling, so that's T2. Friction, the kinetic friction is going to be opposing the motion, so this is going to be presumably sliding down the ramp. So there's also going to be a friction pointing upwards that way, that's FK2. Sorry about the sloppy handwriting. And I know gravity is going to be pointed down, M2 times G. So I've got my free body diagram there. The next step, pick a coordinate system. In this case, I'm going to use my tilted coordinate system. This is sort of a nice thing here is the coordinate system over here does not have to be the same coordinate system here. Remember, we're going to set up a system of equations for each free body diagram on their own. So we need one coordinate system for each of those, and they don't have to be the same. But anyway, moving on. So now it's just apply Newton's laws. We've done 1, 2, and 3. Now it's apply Newton's second law in that coordinate system. So if we start with, might as well go with the x direction. F net x is equal to m2 ax2. I'm adding these number 2 subscripts just to make sure that we're clear that we're talking about mass 2 here. In our coordinate system, the normal force is in the y direction, so there's no normal force in here. We have, if we were to break gravity down into its components, where this is our right angle, this is Fg in the x direction, and this is Fg in the y direction, going down this way. So there is an x component of gravity, and it's in the positive x direction. And what is that? Well, we know that, because we've done a few problems like this before, that if this angle is theta, this one right here, that this angle down here is also theta. So this angle is theta. And again, we've gone over this in the synchronous sessions. If you have any questions on that, we can go through it again. But anyway, if that's the case, I know my hypotenuse, the side opposite my right angle, has a magnitude of m2g. So if I want to know this side opposite that angle, I know that that Fg, the force of gravity in the x direction, is going to be mg sine theta, because it's the opposite angle there. So I have mg sine of theta. And then I have, in the negative x direction, I have this tension, T2, negative T2, and the negative kinetic friction, FK2. And those are the only forces with x components, and they're equal to m2 acceleration in the x direction of 2. So this is one equation that I get from Newton's second law applied to mass 2. The other one from that is going to be the same Newton's second law, just applied in the y direction, m2y. And in this case, well, we have the normal force in the y direction, and we have this y component of gravity here, which is m2g, in this case, cosine of theta. And the acceleration in the y direction is 0. Again, this block here is going to stay on this ramp, and it's not accelerating at all in what we've defined as our y direction. So this is going to be equal to 0. We know that the normal force on the second mass is equal to m2g cosine of theta. So I have this equation for that. So you can see we had the same sort of thing we had when we were looking at mass 1. We have a two-dimensional system. When looking at mass 1, an x and a y direction, we got two equations from Newton's second law that we were able to use, and we actually combined them to make one. We saw the same thing here, where we had two equations from applying Newton's second law to our two-dimensional system in mass 2. What we can do now is the same sort of thing we did over here with the force of friction and this force of friction in that equation. So if we bring this equation down and then plug in that this normal force into our equation for friction, this system of equations for mass 2 can be released to m2g sine theta minus T2 minus this friction's mu k times n, so that coefficient of kinetic friction, times this normal force, m2g cosine theta. And this is all equal to mass 2 times acceleration in the x direction for mass 2. So this gives us sort of the equation we get from looking at mass 2. And now we have two equations, but we have, we actually have T1 we don't know, AX for block 1 we don't know, T2 we don't know, and AX for block 2 we don't know. But we haven't used Newton's third law yet, or any constraints of motion. So what we know from Newton's third law is, this tension, T1 pulling on this end is equal and opposite T2 there. So they have the same magnitude. So we know T1 is equal to T2 is equal to just the tension, right? So these, two tensions are now actually just one unknown. And likewise, the acceleration of block 1 is equal to the acceleration of block 2 is just the acceleration. They're tied together with a rope. If this one accelerates that way, this block is accelerating that way at the exact same rate. So again, these two accelerations are the same. So we can actually, now we have, two systems, two equations, two unknowns. We can solve that. If we want to just rewrite them in terms of those variable names, we have t minus mu k m1g is equal to m1a. That's that equation. Then over here we have m2g sine theta minus t minus mu k m2g cosine theta is equal to m2a. Now, hopefully we can solve this. Two equations, two unknowns. It's just, algebra, but hopefully we can do it. T is equal to m1a plus m1 mu k times g. I can then take this and substitute it in for this t over here, and we get m2g sine theta minus m1a minus m1 mu k g minus m2 mu k g cosine theta, all equal to m2 times a. Let's bring all the a's to the right-hand side and just write this out again. m2g sine theta minus, let's factor some things out here. We'll factor out the m1, or we'll factor out the mu kg out of these. So we have mu kg times m1 plus m2 cosine theta is equal to m2 a, and then can't forget about that term, plus m1a. We can simplify this a bit, but essentially, we're pretty much done. m2g sine theta minus mu kg m1 plus m2 cosine theta is equal to m1 plus m2 all times a. We know all the numbers on this side of the equation. We know both masses. They were given up here in the question. So we can plug in those numbers for this. If we do all of that, presumably we all know how to use our calculators, but this acceleration ends up being 2.04 meters per second squared. And again, I'm not going to go step by step in how I entered the numbers in the calculator, but we know the mass is m2, we know the angle 30 degrees, we know g is 9.8. Plug those all in, we get this. Now the question also asks for what the tension is. All we have to do is plug this back in there, and then we now know m1, we know acceleration now, we know m1 again, mu kg. We could have also plugged it in this equation over here, but it's easier to type those in the calculator. But the point is, plug in the numbers and we can solve for our tension. This ends up being 26.6 newtons. And we're done there. And we've answered this problem. So we take a step back and sort of look at it all together. Seems kind of complicated. This could be a challenging problem. But again, one of the reasons I really like the Knight textbook is it gives a lot of the topics it approaches. It gives you a nice sort of approach and how you can always just sort of brute force your way through a lot of these problems. And no matter what this problem asks, whether it could have given you the tension and acceleration and asked for the masses or something, whatever weird like that, you're still going to go through these steps. You're always going to have to identify the forces that are involved. You're going to want to draw a free body diagram, and pick a coordinate system, because ultimately what we're doing here is we're applying Newton's second law, and we're going to need that coordinate system to break these forces into components, right? And then you're just going to keep doing that, and you're going to get these equations. I'm not really going to ever be over concerned with what these numbers actually are. I'm more concerned that you can use all the things we've been learning in these videos and in our synchronous sessions to sort of model and analyze these problems. So I encourage you to just start working through that. As a whole, this problem may seem intimidating. It's, kind of very involved and can take some time, but all of these individual steps, identifying forces, drawing three-body diagrams, and picking a coordinate system, breaking vectors into components. We've done that a lot. Hopefully we're getting very comfortable with that. If we can remember to just break this down into small manageable steps, um, we should be getting comfortable and efficient at solving these problems. So if you have questions on that, by all means, email me. We're going to be doing more examples in our synchronous sessions, working together in groups. So I will see you then.